All right, so I guess we'll get started. Um, so I think everybody got the message, the memo about the profiles. So actually, there are a couple of reasons why we want to have the updated profiles. I mean, we want profiles to be accurate, and so I think having the first page be the thing that lists just in words the main projects that you're working on, and then second page can be like the most recent result in one slide. Like the thing that if a visitor were to come by, what would be the story that you'd want to tell them in one slide? I think that's what I was suggesting that we can insert. And it could be like some summary of the APS March meeting or some other result, whatever thing that you would want to tell as a story.
Not necessarily the thing that happened last week.
Right, that's right. Yeah, no, it should be a
important, polished, recent result.
That's exactly.
The profile page, right? Not the replay page. There.
Well, okay, maybe what we should do is open up so profiles. So these are the profiles, right? Okay, so I'm just going to close my eyes and I'm going to pick one. Who did I pick? Okay. Where's she? So, so I guess here we have their main project. This is sort of a combination, I guess, of the first and second page that we talked about. So I guess I mean, in some sense, we may be able to combine them like this, but I guess we want to make sure that the other things are also well represented. So basically, the major things that your major projects that you're working on are also represented, at least here. So the question is this, are we already doing what I'm asking people to do? That's the question.
Well, I don't think these are being updated. This slide.
Right.
Are, in most cases, probably a few months old.
Right. So maybe that's really what we need to do, is to make sure that, yeah, especially now after the March meeting, we have all these polished slides and figures that can go in. And the other thing is, it's not necessary to, let's say, have so many words, because the idea is to have figures and major captions, and then the idea is that somebody will then describe what is going on. Okay, so I guess then, to revise this a little bit, let's just have everybody re-examine. Everybody should re-examine, and this should be a 30-minute most activity. Re-examine and think about your profile and make sure that all the major categories are represented. So, okay.
Then what about these weekly, like?
Yeah, well, that's another thing that we definitely want to do. So this is not something that well, I don't see. This one doesn't have a. Oh, this has one. Okay, well, let's look at another one. Yeah, so I think that this looks good, and Yeah, so I think this is basically how it should look. The weekly thing should have, I guess the only thing I would say is that there should be a separation between things that were done in the past week and a list, bullet points of things that you're planning to do in the next week. But, okay. Yeah, and then, right. So we haven't figured out, we haven't decided on a format, but I think it should, at minimum, have, you should be able to know the name of the person and so forth. So maybe the thing to do would be to take something like this and just, to keep this part, and then have this part for what you did in the last week, and then this part would, bullet points would be listing things that you're planning to do in the next week. So why don't we try that for next week? Don't worry about this week, but for the next week, try to format so that you can just copy this slide. Maybe you can remove the colored background and then keep 3/4 of the slide for things that you've been doing, and then this part here for a list of things that you're planning to do for the next week. Okay, let's try that. All right, so April Fool's Day.
So I'll skip ahead to the last slide here. So, since we're talking about the profile of this nature, so Jason Pettis is visiting today. So Jeremy sent out an email last night about wanting everybody to meet with him at between 2 and 2:45 today. I think Jeremy and I had some discussions, and it might be better to have like some small groups meet with him rather than everybody meeting individually. So I just made like a rough draft here of groups based on projects. So, but this is open for discussion. So I mean, basically, I gave everyone like 7 to 8 minutes, and then
yeah, I mean it's like it's approximate. So if it, we don't have somebody with a timer, but there are going to be 5 groups, and I think this is good. So the point is, yeah, you should be prepared to use that time and have. Hopefully, you can take advantage of the slide that's up on the wall, right? So let's get that working. Make sure that that's operational and so forth.
Right, and then I also want to point out that Jeremy's meeting with him this morning. So, they can cover lots of general background information. There's probably things in more detail too, but just so everyone's aware of it.
Yeah, that's right.
From the beginning of the story.
You don't need to have everybody showing like, okay, now here we're writing a wire, now we're cutting the wire, like we do at the March meeting.
Okay, so next experiment. So this is what we showed about 3 weeks ago. We had this exact structure, and we were like, ooh, look at these current oscillations, and they change frequency with time or temperature. So then on Friday, Megan did an experiment where she replaced the sample with just a resistor. So the 100 kilo ohm resistor. You see these oscillations here, and if you make the resistance higher, the oscillation frequency is smaller. Smaller, yeah. Which is basically exactly what happened here with the sample. The sample changes resistance as a function of temperature, so we see this oscillation frequency change. So this really seems to be, it's not a sample, a feature of the sample, but rather something, but we didn't trace down the origin yet, whether it's some ground move or
It wouldn't be a ground
something.
move. But,
Okay.
so, you're acquiring data with a, so you have a current to voltage converter, right? And then you're acquiring with an A to D converter, which is 16 bits.
Mm-hmm.
So what is the quantization level of current for the gain setting? It could
You
be,
think it could be bit noise?
yeah.
Anyway, you are gonna replace
Here.
that.
Yeah. So move on. So we got these 16 chassis. So we have five chassis, 5 controllers, and then 5 each of these cards. There's a 4461, which has 2 24-bit outputs, 2 24-bit inputs, and 5 4462 cards, which have 4 24-bit inputs. All of the hardware seems to test out okay. Greg is going to format these controllers to Windows 7 and put all the value and everything on it. So we got that running on one of the chassis, one that we'll use for the DR200. So it's running Huawei's program. That's about as far as we've gotten, and we're having trouble getting the fingering switch to work. Yeah, but that, I remember that was really.
But the lock-in works well, or it seems to work.
It runs. We haven't done anything like data, even dummy data. But I mean, I was happy that it communicated with the card.
Right.
Pretty much out of the box.
That's great.
We just had to redefine the channel. So when out, these are essentially available for experiments like the closed cycle cryostat. You just want to take 24-bit card, you take it and put it in the other chassis. So you don't have to do any other.
What do you mean taking 24-bit card?
Yeah, you just go to one of these chassis that are up there on the upstairs.
Yeah. But why not just take the whole chassis and use the computer?
He already has a chassis.
Because he already has it'll be much more work.
I see.
Because this, actually, the one thing we were trying to do is to do remote, like a remote interface with this, and as far as I can tell, we can't do it. You have to run the program on this computer. You have to run Labby on that computer. So, if the way you have things set up is you have a computer that's communicating with the Pixie chassis.
I see.
You just drop this in, that computer you can't use it anymore. I mean, you can use it to like TeamView on the other computer, onto the Pixie controller, but that's it. So in the long run, I don't know if these controllers are going to be the best thing. It's kind of embedded controller, but I don't know. And they're not real-time controllers, so that's a different thing where I think you can do, you can use that as a remote instrument, but I don't think this time works.
But you can still probably, have this just work as a lock-in and then have the data be ported over to another computer, right?
Yeah, if that makes sense, if that communication bus is fast enough.
I mean, it should be. It's a very small amount of data once it's processed. I mean, you're not sending the 200 kilosamples per second of 24-bit data.
Well, yeah, but then this is running the lock-in program.
Right. So, but the lock-in program is spitting out a very small amount of data.
Okay. So you just run it, you just start it, let it run on.
Just use it as a lock-in that's always publishing its result, and then you just read it. You sample the data.
That makes sense.
Yeah, I mean, the lock-in produces the data maybe every 1 second. So.
Yeah, so it's almost nothing.
Just, yeah.
Well, you can also configure it to run IV curves and so forth, and it's the same thing. You can just say, you send a command to this computer, which tells it, says, okay, I want to take a curve, and you give it the parameters, and it takes the curve.
Maybe it's already processed by this computer and it write a ITX file.
Yeah, and it just publishes back an ITX file or something. We can think about it.
Yeah, for now, I think, like, the easiest thing for Shushan to do is take a card. Throw it in your chassis.
One of the deck card in the chase of the prosthetic, like, broken, and replace these two. Yeah, that's better.
Yeah. Okay, and then the last thing is the fridge is apart, is what it looks like right now. So we have access to all these upper plates, and we're going to look at sources of electrical noise, which cause us to need a higher temperature. So one thing I should play out was this connector here. So this is this loom goes up to the 50-way connector, which goes to temperature control, and then it comes down and there's basically a little breakout port, and they said to check those connections. And then the other thing is maybe there's some ground loose from the default tube, which we haven't been able to find yet. So that's another thing.
Okay, so last week, one thing is I tested this sample, this canvas, and sent it to case for the microwave microscopy. And another thing is one sample exfoliated graphene or graphite is received. We have 3 samples left or came through, and all the 4 samples exfoliated the disco are also received back. So this is as a reminder.
So we sent 4 samples to Phil Kim's group, and he sent us 1.
Yeah, just
okay.
As a reminder, just want to mention, like, all these tabs are actually into the interface, so all these tabs are connected to the interface. So this is how this exfoliated graphite sample looks like. So they check the 2 spots. This is one spot, check it here. So this one is the graphene. They tested with the Raman, and they know that in this case is the graphene. Yeah, but under the optical microscope, it's very hard to see if there is a graphene or what.
So the slightly lighter color there?
Yeah. It tested with Raman is
okay.
Yeah, so it's for me it's very hard to see.
Yeah, but you should be able to see it by AFM.
Yeah.
Is that other piece multi-layer?
This one should be much less. Right.
And then in between, there's nothing.
Between these two?
Like like here where it's black, does that mean there's nothing there?
Yeah, I think. But I haven't tried it for yet. I started with another place I found here. It's a multi-layer, so it looks bright and the microscope, and also why do they have used this? The thickness of this is around 4 or 5 nanometers, and the interplanar space is more than 10. Yeah. And also another thing is like this the pad size is 50 micrometer times 200 micrometer, and the wire bonding is active, which means this shape works for our wire bonding. And also,
we ever do anything about that tool, about rotating the tool and the?
Yeah, I tried like rotating the tool and also like lowering the force.
Yeah.
But sometimes you can see here.
Did that thing move when you rotated it or not?
It just don't happen.
But does it move? Does it change position relative to the wire?
Which?
Yeah, mostly just neutron over the wire.
Yeah.
Yeah, we definitely would like to get rid of that.
Yeah.
What about changing the angle of the sample? Can we do that?
I don't think that's something we want to do. You should just,
Yeah,
you shouldn't have to do that, I think.
I agree.
Yeah, and here I can show more. Okay, so basically I do experiment with sample. First is test the writing. I first writing between these two electrodes. We can see a conductance jump, although it's very low.
Have some big delta stuff in between the wire.
This one, I'm not sure. Sometimes when scanning this strap, I didn't see this strap. Maybe because something touched on the FFT, so when scanning it shows. Yeah, I'm not sure what this strap is. It may be because like this distance is too far away because the whole image is 80 micrometer times 80 micrometer, so the conductance jump is low. And then I try to write 1 micrometer bar between these two electrodes like this, and didn't see any conductance jump. And then I also try to write in a single wire across the graphite, and didn't see conductance jump. And also I tried it to write it separately, and didn't see like conductance jump.
There's a little bit of a jump.
How about between the electrodes lower left and upper right?
These two?
Yeah, you should be able to see something.
It's already highly conductive.
Oh, it is? Okay.
Yeah,
Okay.
Graphite is conductive.
Oh, it's just a sanity check, that's all.
Okay. Already
I think the problem is that even you wire with the bottom two electrodes, conductance jump is really, really low.
yeah,
compared
but
to
but
you use it.
yeah, I do expect things like say it's like work across the graphite. And then
The graphite grounded?
no, during the writing this one is floating during all this. And then I like scan the images, so the image looks like this, and the profile looks maybe like the chip moves something, and the graphite looks like this. And then I rewrite this nanowire, and when writing the nanowire, these two electrodes are floated, and then I apply the same gate voltage, the same voltage to these two electrodes, and set the voltage to 1 volt, and I see conductance jump between the.
That was after you wrote the wire?
Mhm. But before, if you apply 1 volt before writing that wire, you don't see anything.
No,
right?
no, I checked that. Yeah.
Okay.
Yeah, and after I apply 1 volt, the comes like this, and it goes to like saturate, and then I set the voltage to 0. The conductance jump goes to 0. But then I like just the same. I didn't do more writing. I just the same devices, and then I like redo the voltage. First the voltage is 0, and then I send the voltage to 1 volt. They have this conductance jump, and then set it to 2 volts. The conductance jump actually a little bit lower, and then set 3 volts at this. And the interesting is when I set the voltage to 0, the current is still here, and it's like.
So there's a bistable. Did you go negative on this?
On this one, no, but on next slide I checked. And then because it seems like there is a current between these two, so I think maybe after applying this positive voltage under this graphite there is a 2-deck form. I guess so. So I write in this structure to check. But I didn't see the conductance jump. I'm sorry, I don't know why this data didn't show here, but when I write this, I didn't see conductance jump. So which means, and I measured the current between this electrode and this one, so which means there's no like conducting 2-deck forms under the.
But then how can there be conductance between One, the upper left and the lower right.
Because maybe I think maybe because I'm writing the wire here, so if I apply.
Okay, so maybe it's there, but not.
Yeah, but
That's interesting.
Yeah. Yeah, but.
Maybe it's
What?
Well, it may be that there's a local wire that
Yeah,
it's
because
not
it's a local
that
wire,
it
so,
that it's conductive in the middle, but not surrounding it,
Yeah, that's.
which is very interesting.
Yeah, yeah. Well,
That's actually what we were hoping for.
Oh yeah, here, yeah. This is the conduct in this two electrode. This is after I write this, I didn't see conduction jump, but the conductance between these two is the background conductance is higher than what I see before, like this one.
Mm-hmm. Well, just a little bit higher.
Yeah, a little bit higher. So maybe there is something formed here. But for this one, I write a Y in the middle and apply the positive voltage. There is a conducting channel form. That is what I get from the data I observed. And this one is I applying like negative voltage on this one again. So at first the gate voltage is 0. There's still some background, maybe because the decay is still not decay to 0. So at first the gate voltage is 0, and then I apply 25 volts. There is a conductance jump, and then that is 0. It drops like here and still decaying, and then I set it to negative 25. It goes back to 0, and then I set the voltage to 0 back. The conductance comes back, and I set it to 5 volts, but then the conductance jump is still at this level and the decay. Yeah, and also as I mentioned, like these two electrodes are also actually into the interface, are also connected to the interface. So there may be like some other reasons like leakage between the top and the interface, the side gate effect, almost also means so it's charged. I'm not sure. And then okay, then I erase this the whole area, and this is the profile looks like similar to last one, to this one. And also one thing is after like this writing, I didn't see like it's hard to see like some like leftover features on this graphite layer. And then this one is after the erasing, I measure the IV curve between the source and drain under like different gate voltage. Basically, there is nothing as expected. And then I write in this non-wire structure again and measure the IV curve after applying the gate voltage from 0 to 1 and then back.
How is it that you're getting a No, I don't understand.
The top and bottom graph.
This one is. This one is.
No, not that one.
This one.
No, the two on the right.
This one.
Yeah, that one.
This one is, and then after I do this first.
Yeah.
And then after 0, I set it to negative voltage. This is from 0 to negative 1 volt and then back to 0. Okay. So.
Still have a very large current offset.
Yeah, it's very large offset.
Yeah. The offset is, yeah.
I think there's something wrong with your measurement setup.
The offset is from the channel current line.
Yeah, it's the drain. This is the DC.
Yeah.
Well, no, because you have, you can have a conducting path directly from the gate. The gate is not isolated from the two-dig. So you're getting a lot of current flowing directly from what you're calling the gate through the wire. So that's what you're measuring.
Yeah.
It's not really a gate. It's just another path.
This way I just left the source and drain and raising this again from 0 to 1 volt to 0, and then from 0 to negative 1 volt.
Yeah. So it's very interesting. So I think probably you should maybe look at the single graphene layer.
Yeah. And then what I tried this one, I first write this nanowire and basically apply voltage to this 3D and measure the conductance between these two. Here, this is not the right conductance. I applied 20 dB attenuate between these two. So this is what it looks like. First, this two voltage is 0.
It's really hard to read what you're doing here. Oh, you have so many arrows. Why won't the LAO be a barrier in this case? It seems like it should be.
I mean,
it is.
No, but the previous slide there's all that leakage. Like what?
Oh well, no, but okay. So in those experiments, you have, it's not a barrier because you have a path from the top to the electrode to the bottom. So the top and the bottom are shorted out. If the interface below the graphite is conductive, then you have a path from the top, which is conductive, to the electrode, through the interface to the bottom. So the top and the bottom are shorted out.
Oh, it's underneath the.
Well, this electrode also actually stays the same.
Yeah.
Okay.
So this one is after writing this single wire and applying like negative 5 volts and then negative 10 volts to this wire. After applying negative 10 volts, there is a little bit.
So the question is, did you do this experiment without writing the wire?
No.
Okay, because you don't necessarily know if you're not just getting a field effect from the gates that are 25 microns away.
Yeah.
So you would need to compare this result with.
Yeah,
Here, what is this showing?
This one is basically I do the reverse thing. I apply voltage to these two, and to say whether the voltage between these two needs can modulate.
Okay. Yeah, and the other thing is that if the interface is conductive below the graphite, then you still have a shorting. So if you start applying a gate voltage, it's going to short out and cause a change in conductance. So the problem is that the nature of of how this graphite is situated on these electrodes is preventing you from doing the kinds of experiments you'd like to do. So I would say you should do these kinds of experiments with the graphene. I would say you've seen some interesting effects with the graphite, and I would move on to the graphene.
And after that, I try to erase this area and compare this one to.
Yeah, it looks like you've been cutting graphite all over the place.
Yeah.
All those stripes.
Yeah.
That's probably just bits of graphite that are that have been nano exfoliated from the surface and are all over the place. Which is fine, because maybe we'll use this in the future. If we take a piece of graphene, maybe able to actually cut the graphene, make it isolated and so forth. I think it's time to move on. And look at the graphene.
Well, the last slide is just after this erasing, the starting between these two goes back to 0, so they people this contacting that and also the
Well, we have to. It's 9:40, so.
It's just
we know that other people need to talk also.
So, last week, Mike Summers came in again to work on the VCO. On Monday and so we were able to replace the Pyrex ring that goes in between the depot source and the chamber door. So that's good, and all these screws in here are just hand tight now, so now we won't break it. He was able to find a company that can replace these ceramic ball bearings that go in between these grids. So, in case we lose any of them. On Tuesday, we found some a relay that was just shot in the edge depot indicator, just switched back and forth between them, and also an air hose blew off the high vac valve actuator due to a broken ferrule. So Mike went to Granger to replace both of those, and we got both of them working.
But one of the interesting things here, I don't know if you'll mention this, is that because of this relay that he found, he basically figured out how to switch between the etch and tempo sources, which is sort of a mystery how it completely works, but this is part of that.
It was a mystery because the thing was broken.
Well, we didn't have wiring schematics. That's what the mystery was. But we tracked down this relay here, which is part of the switching, and it happened to be broken. But
Okay.
that's just part of the whole story, which is why I mentioned it.
On Wednesday, we went to look for more leaks after replacing the ferrules in the relay. Just the pressure in the high vac just kind of plateaued at 10-4 torr. So we performed a regen on the cryo to clean it out, and we couldn't, since the cryo what was it? Oh yeah, we had to use a heat gun to cool it down since we didn't have the purge heater connected yet. So after we regen, we couldn't start the cryo compressor because there was basically no power from the APC to control the piezoelectric.
The APC.
It's just this
So pressure controller?
pressure controller, right? Automatic pressure controller. That's what it is. Yeah,
it didn't turn on because it couldn't read the pressure.
Yeah, exactly. It couldn't read the pressure in the chamber, so we needed to figure out what was going on with that. So Thursday, we found out that it wasn't turning on because this connector right here, it didn't have a coaxial connector on it. Like we found that we needed to replace it, and from last time, and so we resoldered this whole thing. It was a massive process because it was just so tiny. But we connected it, and now the cryo pump works. Removed the depot source, cleaned it, and now we can get the process chamber down to 10-5 torr with some fluctuations just from outgassing because the chamber is so dirty. And the high vac's down to 10-5.
Which should it? Sorry, go on.
What was that?
No, go on.
Okay. So we tried closing the high vac, and the chamber pressure dropped to the -2 torr range. So that wasn't very good. And he replaced this O-ring in the target assembly. I'm not exactly sure where that O-ring was, but it was replaced, and we were able to get the chamber pressure down to 10-8.
It was for the cooling water.
It was? Oh, that's
Unless you're talking about a different one, but anyway.
No, that would make sense. That would be where it is. And then we were able to try out the gas pressure, which regulated it. Wait, 10-8.
So that's pretty good.
So yeah.
Those numbers,
Yeah.
2 times 10 to the minus 8.
I don't know if that was for the gas pressure.
Well, the argon should be 10 to
Or
the
the,
minus.
or the chamber
yeah,
pressure,
I-
even 8 times 10 to the minus 8 is very good.
Was 10 to the minus 8 the vacuum, or?
He said the chamber pressure got down to that.
Okay.
Yeah. So I thought that was pretty good. But the argon pressure, that's
When you have low argon, you want 10 to the minus 4.
that's supposed to be 10 to minus 4. Sorry. Copy and paste. And yeah, we're still seeing fluctuations from just outgassing the process chamber.
Yeah, it seems like the vacuum is okay, except for some leaks from when you're taking the sources out. So, but I guess it got down to, did it get down to 10 to the minus 8?
Bro, I don't know if it's completely right.
You don't believe that number?
It seems low, but anyway, the vacuum's okay.
Yeah.
Okay.
Keep going.
So next steps are to find a replacement ion gauge. Just for, I wasn't exactly sure what was wrong with the ion gauge, but
We just want it spare.
we just want to stay out there.
It's working okay.
And then you want to leak check the entire system, just make sure nothing's wrong. And then next time the big thing is to get the unit controller running. Also, Mike, you mentioned that Cornell Nanofab is selling a similar Vico model, so it's something to look into for like replacement parts.
Well, they're getting rid of it. And so,
Are they getting rid of it now?
yeah, whether it's selling or donating, but it's a single source version of what we have. So he just brought this up in case we wanted to look at parts.
So what is the plan for next week, for the next week?
Basically,
Yeah, so I think our opinion is that, you know, it'd be good to bring him back. And he said that the next week he's here, he should be able to begin testing the sources. Basically, that's the point we're at.
Okay. So,
should we go ahead and bring him then?
well, yeah.
Okay.
I mean,
So I think he can probably come next week. I mean, he said his schedule's clear.
so we should just do it. We should make sure it happens. I mean, there's no reason to delay anything at this point. We have a budget. We're still within budget.
Okay.
It's costing about $8,000 a week,
Yeah.
and
Is there a what's the
I mean,
budget?
I don't know how many more weeks we can.
Right. That's kind of why I wanted to make sure it was okay. I mean,
Well, I think we kind of don't have a choice, but we need to look at how much we've spent. We just need to check the budget.
Is there any more parts, major parts that are needed?
um,
No, anything that we can get is probably just at like a Granger or machine shop.
So that
the
is extra.
Venus controller is still kind of a question, and that might be something that would be advantageous for this other
House
system. And then the other option is running everything through a PC. I mean, we were talking about this. This can be a long-term goal anyway, because we can monitor basically everything, pressure, being current. We can do the logic on that. But the plan was to get it working, without trying to integrate PC first.
I mean, does he think that he can get it running in the next week?
I think his feeling is for it to be operational, it would be at least 2 more weeks.
2 more weeks.
But it's still not clear how well the Xenix is working. That's something he hasn't had a lot of time to work on. But I think the Xenix is doing a lot of logic, so I think as we talked about before, we may be able to bypass that anyway. And run things manually if we need to.
Okay. Yes, I think we need to budget the end of this. Need to find out where we are financially, and then so that we don't run into some dead end.
Yeah.
Our manuscript has been submitted to science, and the last time I, excuse me, the last time I checked the status for the submission is still alive, so we're waiting for the response from science. And as you know, I finished my defense last week, last Thursday, and I have some paperwork to do, but that's not very important. And I'm planning to leave this Thursday. So I put this picture here. This was taken, I believe, in 2007 or 8, so many years ago. I was shadowing Patrick for optical measurements at that time. And I just want to say I have fun in this group, and thanks everybody for everything. I wish everybody good luck in the future.
Is that Jeremy flying?
He's a marionette. It was very, very uncomfortable. Because it was one of these things where we were like, well, let's do something different for this photo shoot. Oh, why don't I just like hang me up? And of course we didn't have something that was, it had like really thin rope. Cutting off my circulation.
Get rid of the ropes.
Oh, that's right. You can actually see them. Yeah. It's up there for like 45 minutes.
Last week we characterized some different like simpler devices. So like this one is just a single junction device. And in the 2 terminal we did see we applied some negative backgate because when it cooled down, this gate was leaking very quickly. It had a very small tunability range. Within that range, it wasn't able to do very much. So we applied some negative backgate to increase the tunability of the gate. And so we saw similar type features that we were seeing before in this 2 terminal, although in the 4 terminal it was just really noisy. But it doesn't.
Well, and featureless. I mean,
it seems like it's featureless. If there are features, they're in them. But so this probably indicates then that there might be whether it's due to applying the negative backgate or whether it was even there before. I don't know. It seems like that's indicates there's something going on outside the main channel. So in this one, this device, we didn't cut it. This was just writing a gate, sort of trying to characterize our different ways of writing gates, looking at trying to like not let them be connected, but at the same time not hurt the main channel. So with this one, we used an erase box at the end of the gate. This was 25 nanometers, 25 nanometers from the main channel. And
I also don't see any
so yes,
Coulomb diamonds or anything like that.
Yeah, so this doesn't have any features. It did, at room temperature, we did see a drop in the gate, or in the main channel conductance.
But there's no barriers in the wire. Well, there's only one gate.
Yeah, so there's no intentional barrier.
Yeah.
Yeah.
Oh, so
So we
this is
did
not.
see a drop in conductance at room temperature that was equivalent to, or actually I think more, than what, like when we do the gate, or when we do the cutting to create a barrier, we look for, a certain percentage drop in conductance.
This is not intentionally cut.
So this is not intentionally cut, but we did see a drop in conductance when we did the erase to try to reduce the leakage.
But that vertical axis in those images are from the gate, the side gate, right?
Yeah, this is sweeping the side gate.
Either completely insulating in the bottom, I think. Not totally insulating.
Here? Is this the region?
Yeah, can we tune it to insulate space?
It doesn't look like it, no. The closest, I guess, is in the 4 terminal here. going insulating, but in the two terminal it's not, so that's just a leak starting to go bad.
Yeah, but there are also no oscillations, no Fabry-Perot.
Right.
So you have two good control experiments with single junctions. I think this is good.
Well, yeah, this one doesn't have a junction.
Well, it has a side gate, which is
So it's but
a single barrier, right?
Well, I think the problem is it didn't tune it to insulin state like the two terminal in the two terminal.
although I guess if this doesn't have a barrier, maybe that's okay. Maybe if there's a barrier, it would be able to.
Yeah, I mean, the point is that you still have a local disturbance, and you don't have two of them, and so there's no interference. It looks... I'm sorry? Oh, is he not coming in?
I didn't know if you wanted to.
Hi.
Yeah.
Sorry, just have a seat. We're just finishing up our group meeting. If you want some coffee, also this one.
Go ahead, just
Yeah, so that's this one, and then we did another type of. Oh, this was doing the same type of thing within a raised box, 25 nanometers away. This time we were trying to characterize the barriers by as we were cooling down. We were taking IV curves. First, looking at the main channel, normal like 4-terminal configuration of the main channel. And so we got a 2-terminal and 4-terminal activation energy. And so in this device, the 2-terminal
Oh, so you were able to characterize the activation energy as a function of the gate?
Possibly. Well, the 2-terminal went insulating before the 4-terminal.
Oh, okay.
So there's probably a barrier somewhere out.
But that's still interesting. So you're getting, in the 4-terminal, you're getting 3 millivolts.
Mm-hmm.
So you have a bigger barrier, so that one obviously went insulating first.
This is the gate is a second cool down.
Oh, okay.
Warm up cool down, but by the time the main channel somehow is insulated, so
Okay.
you have to cool down.
Yeah. So once we did the temperature cycle, the whole device has changed in phase. It's hard, yeah. So yeah, it's hard to compare the gate to the main channel cutting. And again, here we didn't intentionally cut the main channel. So and then in this device, we did cut the main channel. We wrote the main device, the main channel and the portion wave first, and then we used negative voltage to cut across the main channel, again, 25 nanometers away. And then we started writing with, and then once we did the cut, then we started writing with 8 volts for the first micron, and then 20 volts for the rest of the gate. So this time we were writing the gate in the direction away from the main channel. And we did the cool down looking at the main channel again. And here, the device was really conducting and it never actually went fully insulating when we cooled it to 2 Kelvin. And it has a very small barrier. So it seems like the main channel here is good. We weren't really able to increase the tunability of the side gate by changing the back gate. These are a different back gate. Sweeping the side gate across here and monitoring the current. And so at negative 2 volts, negative 2.01, negative 2.05, and negative 2.07. So at negative 2.07, it's tuned insulating for the most part, but
Right. Negative
the whole thing is
2.06.
insulating. What?
Negative 2.06.
I just don't have it.
And yeah, it's interesting that there's a certain range.
Yeah, so
Very
the
sensitive.
range isn't really increasing much. The whole conductance is dropping more.
But I mean, this method looks interesting enough that it might be worth trying to have a double junction, you know.
Yeah, so we want to probably cut a larger barrier, because this one we do have a barrier that we tried to cut in it, so we weren't able to get it. We weren't able to tune it insulating the gate. we probably want to do a larger area. So this is just sort of summarizing what the first approach would be, like last approach. And then, yeah, I'm just going to point out that in neither of these approaches did you see the any type of cooling back features as we went explain.
Good.
So like any of those oscillations.
Okay, great.
Most of this ecosystem we already talked about. The system for monitoring these parameters that Michael Summer suggested is DeviceNet, but I think this is just what they're using in Pico. And then I was working on the manuscript more fundamentals for connectivity, and the story here, as well as that in the March meeting talk, was cross-Andre reflection or elastic co-tunneling as a signature of coherence link. Based on feedback from that and some deeper analysis of the data, it seems that it's not so clear that we see this, that maybe everything we see is just explained by charge amount. So I spent a lot of time studying this and looking at the data some more. So basically, charge imbalance are measuring a chemical potential difference between quasi-particle excitations in the superconductor, and you get the phase flip centers in weak links, magnetic impurities, and without necessarily the need for normal electrons. What we had been looking at before is CAR and EC, which should dominate over charge imbalance at low current bias, and as T goes to 0. Because the length scales in these processes are much shorter than charge imbalance, a way to distinguish these two that has been done in the literature is temperature dependence of the zero bias non-local resistance actually at different channel lengths in the non-local case. Now this is a data set we don't have, but what I did look at something similar in the magnetic field dependence. And basically, I think it's not clear that there's anything other than charge imbalance based on this analysis. So this is a plot of non-local resistance versus field. So I think you can see this white line here is a cut here. And then red and green, I'm comparing it with the high current minima. So the idea is that the high bias, this is above the critical current, should all be from charge imbalance. And then maybe any contribution from these other processes would show up at zero bias. So at zero bias, there is a maximum around the critical field, but I don't think this is really very illuminating. I don't think it allows us to eliminate charge imbalance. Temperature dependence in another device. Basically what we see here is...
what's that scale?
Here? X or Y. Sorry, this is temperature in Kelvin. And then the y-axis is non-local resistance in ohms. So the blue curve is the zero bias non-local resistance. The yellow curve is when the current is greater than the critical current.
It is the maximum not right at the critical temperature.
The critical temperature in this, it is at the critical temperature in this device,
Okay.
or just below it. Yeah, I mean, I can show you a plot of them together. But, anyway, the point is that it's with the data we have, it's not, we can't eliminate charge imbalance. I mean, it looks like it's quite possible everything's...
I mean, I'm not sure what you're comparing here.
Yeah, this plot is, I don't want to spend too much time on it, because it's not plotted very clearly. So basically, I wanted to show that analysis that I had done, and I think that maybe the story should be reworked a little bit to place less emphasis on this coherence question. But this charge amount maybe can also explain why we measure different local resistances, at least the mechanism by which we're measuring different four-terminal resistances locally too. But that's something I have to look at.
Okay. So I guess that's it, right?
Yep. When you're in a, on creating